The chi-square goodness of fit test asks whether one categorical variable follows a specified distribution. We compare observed counts to the counts we would expect under the null hypothesis. This test can be used for settings like blood type frequencies and Mendelian inheritance ratios or market share distributions. The question is whether the observed distribution matches the distribution predicted by the null hypothesis. This image summarizes the overall idea of a goodness of fit test. Suppose there are k categories with null proportions, p sub 1, 0 through p sub k, 0. The null hypothesis says the population follows that specified distribution, and the alternative says that at least one category proportion differs. The assumptions are that the data are counts, the variable is categorical, the sample is random, and each expected count is at least 5. For category 1, the expected count is n times p sub 1, 0. These expected counts come directly from the null distribution. The chi-square test statistic adds up the squared differences between observed and expected counts, scaled by the expected counts. Large values indicate a poor fit to the null model. The degrees of freedom are k minus 1. The p-value is always taken from the upper tail because large chi-square values indicate evidence against the null hypothesis. This test is effectively one-sided because the statistic uses squared deviations. Counts above expectation and counts below expectation both increase the chi-square value. If the overall test is significant, we often want to know which categories are contributing most. One option is to examine confidence intervals for the individual category proportions. When many intervals are built at once, the chance of making at least one mistake increases. The Bonferroni method controls this by dividing alpha by the number of categories. Each Bonferroni interval then uses confidence level 1 minus alpha star, where alpha star is alpha divided by k. For example, if alpha is 0.05 and k is 5, then alpha star is 0.01. Bonferroni works because the probability of at least one interval failing can be bounded by the sum of the individual error probabilities. It is conservative, but it protects the overall error rate. In example 1, Mendelian theory predicts a 9:3 to 3:1 ratio. The observed counts are 900, 320, 380 out of 1,600 offspring. The null hypothesis sets the 4 category proportions equal to the predicted Mendelian values. That gives expected counts of 900, 300, 300, and 100. When we compute the chi-square statistic, we get about 5.33. With 3 degrees of freedom, the p-value is about 0.1490. We fail to reject h sub 0, so the observed counts are consistent with the predicted Mendelian ratio. This image shows the jump output for the goodness of fit analysis. If we want Bonferroni intervals for the 4 categories, we use 1 minus alpha star equal to 1 minus 0.05 divided by 4, which gives 0.9875. So each interval is a 98.75% confidence interval. This image shows those Bonferroni intervals and jump. The main ideas are that goodness of fit compares observed and expected counts. Large chi-square values indicate lack of fit, and Bonferroni adjustments are useful when examining multiple categories after the overall test.